Rational functions and discontinuity. What we're going to be doing is a three-part video set. We're going to be looking at how to graph the more complex rational functions. For example 1, we're going to start off with f of x is equal to x squared minus 4 divided by x minus 2. Okay, the way that we're going to approach this, because there's a lot of details that go into how to graph these, in fact, it's a three-part video set, what we're going to do is use the calculator to get images of different graphs and little by little pick up more information. Okay, so we're going to start by graphing this in the calculator. All right, I've already put it into the calculator, and I've even set my window so it best fits what I have here. Okay, let's go ahead and hit graph. And be underwhelmed. Apparently, this is just the graph of a line. Despite how complicated it looks, this is literally just the graph of a line. But there is one little detail about it you can't actually see in the graph that will be important. Okay, so first let me justify why this actually looks like a line. If we take the function that we have and factor the numerator, which is the difference of squares, we get x plus 2 times x minus 2. And x minus 2 is a factor in the top and the bottom, which we can cancel. So ultimately, this simplifies down to x plus 2, which is a line. It is a line that has an intercept of 2. It has a slope of 1, up 1 over 1. And that seems to be all we get. Okay, comparable to the graphing calculator, we do have an intercept at 2. The slope of 1, you can't quite see it here. You could go to the table of values and verify it. That would be possible, but this is a picture of it, except with one difference. See, if we go back to the original function, which is this, okay, before simplifying it, if we go back here and we talk about the domain, there is one value that this function can't be. X cannot be equal to 2. Because if you put a 2 into this, you're going to end up with a 0 in the denominator, which is going to make it undefined. Okay, now you can't see that in the graph, but if you go to the table, you're going to notice that at 2, we actually get an error because it would be undefined if we plugged a 2 in. Okay, so in the graph, you can't see it because it's this instant spot. It's this instant spot where the graph just disappears. But what we can do to really highlight it in the graph is we can go over to where x is 2, follow it up, which appears to be at 4, and we can draw an open circle, which we refer to as a hole. This graph has a hole. Overall, the graph appears just to be a line, which would be y equals x plus 2, except it doesn't exist at that one point. You actually have a hole. All right, for this next part, I've already mentioned it, but let me just go ahead and be very explicit. For a value of x that makes the denominator 0, the function is undefined. Okay, and that's what we had here with the 2. When the factor involving the variable cancels out from the denominator, the result is going to be a removable discontinuity called a hole. Okay, so what's important about creating a hole is that the factor that would have caused the 0 in the denominator, which is the x minus 2, that happens to be a factor in the numerator as well. When you have that case and they cancel, you still have the discontinuity at that number, but it becomes a hole in the graph. Example 2, we're going to create our own rational function that has a hole at x equals 5. For that to be possible, we're going to need to have a factor in the numerator and denominator that would cancel out, and that factor would need to be the factor that would create a 0 if we were to plug 5 in. So that factor is going to be x minus 5. Okay, now the most simple graph that we could do here would be this, just to make sure that that factor is in the numerator and the denominator. Okay, and then it would cancel out. But when it cancels out, what would be left behind? Okay, well, if everything in the numerator matches everything in the denominator, it's going to reduce to a 1. this actually becomes y equals 1, except that it will have a hole at 5, okay? So the graph y equals 1 would be a horizontal line here, but it is going to be undefined at 5. We're going to get that hole. Okay, you can be more creative with this. You can take this as a template and just add in an extra factor. Okay, the easiest would be to add a factor to the numerator. Let's do x minus 3. Okay, it doesn't have to be a conjugate with the other one, which is the main thing I'm pointing out, because that's what we saw in example 1. It doesn't have to be a conjugate. We just have to show that these are going to cancel out to create that hole. Okay, so this is a graph that would also have a slope of 1 with a y-intercept at -3. Okay, so we can put a dot here, 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 and continue on. Except right here, where x is 5, that would be your hole. All right, so what happens when that factor that causes it to be undefined does not exist in the numerator? What happens in that case? Okay, let's take a look at g of x. We've got x plus 4 over x squared minus 6x plus 9. What we're going to do is go ahead and just factor the denominator. Okay, so g of x is going to be equal to x plus 4 over what would factor into x minus 3, x minus 3. Okay, so this is going to be undefined at 3. X cannot equal 3. Okay, in this case, because these factors don't match any factors in the top to cancel out, we're not going to get a hole. We're going to get something different, which is an asymptote. We're going to get an asymptote here. Okay, now we're going to let the calculator graph it, okay, because this is a building process to figure out how to identify certain characteristics, so eventually we can graph these on our own. All right, so again, I've already got it typed in. We're just going to go ahead and hit graph. And this is the picture that we get. Okay, maybe a little bit hard to tell here, but if you were to go to x equals 3, the value that makes this undefined, if you were to go there, you're going to notice, if you were to follow it up, you're going to notice that the graph is approaching from both sides. It's starting to level off as it gets there, which is that asymptote that we're going to get. So we have a vertical asymptote at x equals 3. In addition to that, we do have a horizontal asymptote at the x-axis. We haven't really discussed that yet, but we do happen to have a horizontal asymptote at the x-axis. And as far as the rest of the graph right now, what we're pretty much going to do is just sketch it. We're just going to sketch what we think it is. Okay, and as we go through all these videos, we're going to pick up a little bit more information to make these graphs look a little bit better. But we're going to sketch here. Okay, so we have an asymptote over there. We're also going to have an asymptote over here, and it's going to appear to get closer to the x-axis faster than the other one did. I do want to make one additional point that sometimes gets overlooked. This graph is going to contact the x-axis. It is going to contact the x-axis, which means that it's going to contact the horizontal asymptote. And it's going to make contact at -4. It's going to make contact over there. Okay, and the reason that we know this is because if you look at the numerator of the function that we start with, if you were to plug a -4 in here, you're going to get a 0. In addition, if you plug -4 in here, it's still defined. So you're going to get 0 divided by something, which means your output is 0. You are going to be crossing the x-axis at -4. We can look at that on the table and see it there. Okay, so what the graph does is it approaches as an asymptote, it makes contact at -4, the graph dips just a tiny bit underneath it, then it comes back up to that horizontal asymptote. Okay, so we do have a point here. It's going to be very, very subtle. Okay, it's going to make contact, it's going to go underneath it, and then it's going to come back to that horizontal asymptote. In summary, in a rational function like g of x, when that factor doesn't cancel out the number that would cause it to be undefined, you don't get a whole, but you actually get an asymptote. For example 4, we're going to create another rational function, but this rational function is going to have an asymptote at x equals 2. That would be a vertical asymptote that we're looking at here. Just to be specific, we also want a whole at x equals -3. Okay, so let's build this. We'll go ahead and call it f of x. To have the whole at x equals -3, you're going to have a factor on the top and the bottom, which is going to be x plus 3. So if -3 was plugged in, you would get zeros. But these are going to cancel, which is going to create that whole. In addition to that, we want a vertical asymptote at 2. So that means we need another factor in the denominator that does not match a factor in the numerator. That factor is going to be x minus 2. That way, if we plug a 2 in that, we get a 0. Okay, now you can add more things to this. You can definitely make it more complicated, but this would be the most basic graph that we could think of. And as before, I've already got it typed in, so we're just going to graph and observe. You're not going to see the whole, but you are going to see the asymptote at 2. In this case, the asymptote that we got, the right side is going to go up forever, the left is going to go down forever. Later we will talk about how we're going to know which way the graph goes along that asymptote. But for today, this goes up and that goes down. In addition to this, we are going to have a whole at -3. For that, I'm going to go to the table, and we see it there. Okay, we got that error. Okay, back to the graph. We do have a horizontal asymptote at the x-axis. In this case, the graph is not going to cross the x-axis. All right, for our asymptotes, we're going to draw one here and here. The graph is going to be in this corner, as well as this corner. But in addition to all of that, we've got the whole right here.
Wait, there was.